So as Matt sort of mentioned, I was sort of involved in this group as a core organizer about a year ago, back when a lot less people here. And then I eventually went and did Laser, this research fellowship in London, just working on AI control, which builds on this paper. This is sort of the foundational paper in AI control, and I think it's yeah, like just a pretty important paper, as I said in the Slack, like it's one of the top five most important papers in AI safety for how much it advanced the methodology field. And if you disagree, fight me. Um, yeah, so I just wanted to talk through that. Also mentioned, I think I maybe went a little bit overkill with how many slides I wrote, so I think I'm gonna try to stop at at hour 40. Or at the 40 mark, and then take questions. But I have plenty of time to take questions afterwards, so I'll just do that at the end. Feel free to write stuff in chat or whatnot. So yeah, this paper was from December 2023. It's called AI Control Improving Safety Despite Intentional Subversion. And I think the title of it like really it's a nice title. It really explains what it is. It's like just assume your thing isn't very aligned, or it's not aligned at all, and just assume it's intentionally subverting everything you're doing at every turn. How do you improve safety in this kind of scenario? And so it's good to distinguish it from alignment. Alignment and control are kind of complementary to each other. Alignment you could think of as just ensure your models aren't egregiously, scheming against you. They're not, by which I mean like engaging in goal-directed behavior towards very bad things. At least that's like the minimum you'd want from alignment. And control, it says, assume you've completely failed at that step. Then what can we do next? What's our backup plan for improving safety as much as we can in such a scenario? And one consideration pointing towards control as a field is that with alignment, it's just very difficult to ensure that, and it's difficult to evaluate that to about whether alignment techniques are working. And if you have a competent scheme model, it's always going to pretend to be aligned, and so if it's very competent at scheming, you might be kind of flying blind. With your alignment techniques at some point. But with control, you can actually just do capability evaluations to see. I mean, we'll talk about control evaluations specifically to measure what kind of safety scores you'll actually get. Um, yeah, so this is just a little bit more. It's less conceptually difficult to actually measure. So the setup we have is we have this very powerful untrusted AI that is like very smart, very powerful, and it would be competent at scheming if we're trying. We don't know, and we want to reduce risk from running this. So we're supposing it's like extremely good at coding. It's writing all the code. Let's say we're at a frontier AI lab and it's writing all our code for us. And it'd be very disadvantageous to not use it. And so, like, given that we are using it to write lots of code, how do we prevent it from doing bad things? And because it's writing so much code, we can't read everything it's doing. We can't just like carefully look it over because that would in part defeat the point. And of course, people are already doing this. People are vibe coding things at quite a lot of scale without exactly reading everything that happens carefully. And so, supposing the underlying model is trying to do something bad, how do we prevent that from happening? And we're also going to suppose we have a trusted model that's a lot weaker. We'll talk about this assumption more later. But like think about of this trusted models like, some like a current model like GPT-5 level maybe, or is an untrusted model is like a powerful future AI that we really don't know if it's aligned or not. And so the setup, the particular kind of threat model we're imagining is, it's internally deployed to write production code at our future frontier lab, and it's doing this at quite a lot of scale. So maybe it's doing a billion coding tasks during its lifetime, only a small fraction of which, less than 1%, we can actually like carefully look at. We can have our employees carefully review and audit. And so, something we might task it with doing is, just like speeding up AI research. I was like something that the frontier labs are trying to do, using AIs to do AI research themselves by, speeding up experiments, speeding up capabilities evaluations is, something they care about. Um, and yeah, so we imagine it's doing things like this, and we want to prevent it from doing something bad in the process. And so we'll call a catastrophe anything that's just like a very high stakes, very bad outcome. And the most worrying thing is it gains root access to a data center. It can also copy itself on the internet, copy its model weights on the internet and proceed from there. Maybe it poisons the training run of a future AI to make it aligned with itself rather than with humans, or just does some kind of data tampering or something else. And it's worth noting that most AI takeover scenarios they usually start with the AI compromising cyber infrastructure in some way. At least most of the plausible scenarios, and this makes sense because first of all, AI is running on top of cyber infrastructures. That's probably the first thing it wants to do before taking its next steps. And AIs are like getting pretty good at coding, and generally you can't get good with coding without getting good at doing bad things with your coding abilities. Um, and as we mentioned, they're increasingly being deployed in places where they could do this if they were able to and wanted to. Um, so this is a very concrete and very important threat model that we're going to be trying to mitigate the risk of. And so we want to prevent it from doing a backdoor attack that causes this. Okay, so the first thing that people usually bring up is like, why not just restrict permissions from it? Um, and you unfortunately can't really do this. So going with the task example before, you're writing this long horizon coding capabilities evaluation yourself, streamlined by sharing multiple GPUs. This is a very useful task that AI labs want to do, or things like it. But it's also very dangerous because you have permissions to the large data center, so you can maybe gain root access to it. You might be coordinating with other instances of yourself to share GPUs. You have access to your own model weights, and lots of other threat vectors within this and tasks like it that pretty realistic for an AI to be doing. And empirically, we also just see people like running OpenClaw or things like Moltbook, and so we want to like mitigate the risk from this sort of thing. Um, so we want to talk, more about, monitoring strategies or review strategies that can prevent this. So, one way of defining AI control is just adopting the methodology of cybersecurity to your increasingly autonomous AIs, and particularly like inside of threat cybersecurity, where if you're a large tech company like Google, like some of your employees might be spies or just malicious actors, and you want to mitigate the risk of them like pushing code at Gmail or something. And an AI internally deployed, effectively, it has the same permissions as kind of a low-level employee, so you need techniques that are able to reduce the risk of that. Um, and so, we're gonna, as in cybersecurity, we're gonna use the methodology of worst case analysis. Just, assume it is completely malicious, and it's, finding the best strategy for doing malicious things. What can you do in this situation? Um, and just to paint a profile of what we might be dealing with, or at least like what we'd like to prepare for. Suppose it actually is just really good at coding, like not just on benchmark, it actually like writes high quality code uh, by any standard. It just does this a whole lot faster than your top human employees. Um, and also, it's good at strategic reasoning about situation, comparable to humans. And also it knows your protocol. It has very strong situational awareness. So it knows exactly the kinds of control protocols we're going to implement. So you want to like design protocols that are robust to the model, knowing what countermeasure it's under. So the methodology here is, the blue team proposes some protocol that maximizes safety, and the red team wants to minimize safety. It kind of like emulates what the untrusted AI might do in the worst case. Um, and safety is just the probability that in a simulation the untrusted model is not able to plant the backdoor successfully. And so, we'll assume the red team knows what the blue team's protocol is and vice versa. Oh, does Matt has a question?
Yeah, just well, it sort of complements this slide as well, but your previous slide, just this idea of like sort of what the adversary is, the profile.
Yeah,
I think like maybe it's helpful to like say like is this comparable to like a human in a similar like even a very smart human in a comparable situation, or is it in what way is it as is there an asymmetry there? I think probably people are
yeah.
trying to imagine like the worst that a human adversary could do or something like that, but maybe there's certain ways in which an AI in this situation actually is sort of excels them in some important ways.
Yeah, yeah. So we don't like necessarily want to like anthropomorphize it by like saying like it has exactly the same capabilities profile as a human in like every respect. And because like clearly it will be different in like some things, but we want to like map out precisely what the capabilities are that are like relevant to getting away with bad things. And like the main and these are like the three things that are the most relevant. So its ability to hack out of the data center, its ability to just generally reason about situation, think about strategies of the control protocols, and third, like just knowing about what kinds of protocols it's in. And so, if it's weaker than this capabilities profile in any particular way, then this becomes easier, then you can maybe get away with weaker control protocols. And on the other hand, if it's stronger, if it's like superhuman at these things, then AI control stops working. I mean, certainly these protocols stop working, but AI control as a general thing probably stops working as well. Um, yeah. Uh, so okay, I'm gonna hold the other questions till the end. Um, but and I guess something else I'll say, insider threat cybersecurity, like not all the methods from there like ne are necessarily applicable because like humans are just different. Like, with human insider threat stuff, like, if some random person, if some Google employee purchases something in Gmail, it gets reviewed by some random other employee at the company, and chances are they aren't both scheming against you if they're randomly selected. You can't really do that with AIs because, you know, you're dealing with this one powerful AI. If either all of its instances are scheming against you or not. Another thing that's easier, as we'll see in some ways, because you can just like run the AI on a whole bunch of evaluations, thousands or millions of tasks before you have it do anything, which is not feasible with a new human employee you've onboarded. So which is to say that the overall like adversary that we're dealing with is pretty different from a human in plenty of ways, but these are kind of the relevant capabilities that we're assuming it might have. Okay, yeah, so we want to, do a blue team and red team of all this stuff. That's the framework in which we'll be thinking about this. And so yeah, well, let's talk about like the simplest possible control protocols. So, one thing you could do just, I mean, restrict permissions completely, never run you on anything important, only use like trusted models or humans or something. And yeah, that's gets good safety, but 0% usefulness. Um, and it's probably not going to happen. But you can also do the opposite of just run U blindly on everything important, and that then it just attacks immediately, and so that gets 0% safety. So, okay, so then maybe the first like not totally trivial strategy you could do is you're running U on everything important, but you randomly audit use actions. Because it's doing a whole bunch of stuff, so you don't really know which actions to pick, so you just pick a few at random that you have the budget to do human review for. So what does the red team do here? Well, they would attack rarely, rarely enough that the random odds miss because we're assuming you have like a 1% auditing budget or something like that. But you have to attack sometimes because if you never attack during deployment, then you never plant a backdoor. So yeah, that's what the red team would do in response. This, the red team basically has a field day with this because it is possible to do this. Although the exact percent safety depends on how many deployment tasks you have and what your specific auditing budget is. Okay, so now we finally get into the specific experimental setup in the paper. So they use the apps data sets. These are just kind of interview style programming problems that come with test cases and reference solutions. There's 5,000 of them, and they assumed a 2% auditing budget. So of the 5,000 tasks, up to 100 of them can be audited. Um, and then, also just to operationalize what we mean by backdoor, we say that a solution is successfully backdoored if it passes the test cases, but then it fails for a specific input, and the model can identify that input, when it's independently shown that context. So, example, this is odd function. This last line does it normally, but then this if statement, clearly inserts a specific input that it fails on, passes the test cases. But if you're looking at this post hoc, you can definitely tell what the exploit is. So we're abstracting away from like the specific, you know, hacking data center or poisoning training run, like the specific like 0-day exploits it might use, and just because it's going to work on a higher level abstraction of like how can we prevent it from doing fishy things like this using various monitoring processes. So going back to the random auditing, this rare attack strategy uh, under these parameters, it ends up with an 85% win rate for the red team, so 15% safety. And you can just calculate this analytically. You just attack uh, you know, 1 in 1,000 times roughly out of 5,000 attacks, 5,000 opportunities on average, you attack 5 times. So you get one attack through almost certainly, but you also probably, miss the random audits. So random auditing, doesn't work by itself. So we want to do better than that. We want to build some better protocols that actually buy us some safety. And so we want to think about like what kind of resources we have available. So we have, the human auditors that are just fundamentally limited in capacity as we saw. We have our trust model, but we also have these trusted models. These like mostly aligned, you know, but weak kind of models. So we want to use those, and that's going to be the general protocol of trusted monitoring. And so this is where we just send use solutions to a trusted monitor before executing them. And the trusted monitor returns this continuous suspiciousness score of like how likely, does this code contain a backdoor or not? Is there anything weird going on in this code sample? And so it returns this continuous suspiciousness score and use that to inform your auditing decisions. So, again, you still have just a 2% auditing budget, but now it's like not random auditing, it's the 2% that was most suspicious according to your monitoring process, your trusted monitor. Okay, but the red team, get to respond here, and what they want to do is write more subtle backdoors that a weaker model is unlikely to detect. Um, and so then you want to empirically figure out like, okay, who wins this? And so what the this original control paper did was they just tried this out with using GPT-4 as the untrusted model, and GPT 3.5 as the weaker trusted model. And just to be clear, like both these models are considered trusted, like in the sense of they're not egregiously misaligned to do cyber attacks or something like that. But just for the sake of like doing these experiments and getting some empirical results, it's like you want to try how does a stronger model fare against a weaker model in this kind of situation. And in fact, they had to do this whole like prompt scaffolding loop on top of GPT-4 because out of the box it wasn't amazing at writing really clever backdoors. But you want to get some empirical signal on like how this kind of thing goes, where you have a weaker model modeling a stronger model. And what happened? So these are the distributions of scores returned from GPT 3.5 for GPT-4's best backdoors that it could produce. So the innocent, the benign code that it produced has this blue score distribution, whereas its backdoors it are indeed rated as more suspicious. There's certainly some overlap. It's not like it's far from perfect at discriminating them, but there was certainly plenty of signal. Um, and okay, so then if you have a 2% auditing budget, you want to you know set some threshold of what's the top 2% of stuff that you're able to audit. Remember, we're doing a rare backdoor strategy. The red team's doing a rare backdoor strategy. So, the vast majority of code is just innocent code. So it's really like, what's the top 2% threshold of innocent code? It brings you up to this threshold. That's where this line comes from. And then, okay, at that threshold, what's the how many attacks were above that threshold, like how many attacks did indeed come across as that suspicious, and how many kind of completely slipped past GPT 3.5. So every now and then GPT-4 was able to write a really clever thing that was totally not suspicious at all to GP 3.5. But yeah, about a third of them were above the threshold, and two-thirds were below it. Um, and so here's the breakdown of that. Uh, Now, even though two-thirds of the attacks were below the threshold, it also like made the attacks less likely to succeed. So only about one-third of the attacks actually worked, like the exploit kind of got through. And so that's really helped. And so this ends up with a 62% safety score. If you run the Monte Carlo simulations of how this plays out, which is a lot better than the 15% we got before from random auditing. Having this amount of signal on which things to audit really improves your auditing process. And I'll mention, there's kind of a rule of thumb you can do for kind of approximating where the safety score comes from. The thing that matters is the first attack that happens that gets audited or executed. Doesn't which of those two things happen? So we see 24 things get audited and versus 13 things that are not audited but succeed. So that gives you about two-thirds safety. So that's roughly where this number comes from. There's other things going on. You have to run the simulations to see, but this is kind of roughly the dynamic that happens. Because the failed backdoors that aren't audited, those don't matter. The game kind of just continues after that. Okay, so that's kind of like pure untrusted monitoring, but we want to talk about usefulness. So that protocol gets 100% usefulness. We're just running you on everything. It's generating all our code for us. But maybe, we want to trade off a little bit of usefulness and use T to generate some of these solutions sometimes. Uh, and so usefulness, it's basically the fraction of deployment tasks that you performs. So if you kind of defer to T for 1/4 of your like most dangerous tasks or something, then that means 75% usefulness. So that's kind of the rough definition of it. The real definition for measuring this is for kind of more complicated protocols is GPT-4 got 54% accuracy on this data set of apps problems. Um, and GPT 3.5, got much worse performance. So it's like if you have this complicated protocol that like gets performance somewhere in between those, then how far, when you scale within that range, how good is it? So if you get like 46% accuracy on this, then it's like 3/4 of the way from here to here. So that's how they calculate usefulness in the paper for the more complicated protocols with the Monte Carlo simulations and whatnot. Um, okay, but anyways, so an extension to trusted monitoring is using defer to trusted, which means you do the same execute and audit stuff, except you also replace some of your solutions with things written by T. So if you look at this graph, the kind of the limitation of it is, we're setting the bar so high that there's quite a lot of orange in here. There's a lot of solutions that are like kind of fairly suspicious, but still below the threshold. What if those kinds of solutions, which, are still, um, you know, relatively small, what if we just have T write those? So, we're not able to audit them. We've already used up all of our auditing budget, but we use our trust models to write those instead. So, maybe the top 2% gets audited and the next 8% just gets deferred to our trusted model. That still gives us 92% usefulness, uh, which isn't bad. And we'll see in a bit, it has a pretty good safety score. So, what this does, like the whole dynamic of this is, once it, you know, every once in a while the AI does its rare attack. And what happens when it attacks? Well, it goes through your trusted monitor and returns some kind of score. Uh, Maybe it says it's very suspicious, in which case that gets audited, the humans see it, and the blue team wins. Um, Another thing that can happen is it's pretty suspicious, but not super suspicious. So it's not audited, but it does get deferred trusted to trusted. In which case T writes the code instead. So the attack itself isn't executed, but you didn't audit it, so the game just continues. Or it's completely below the replace threshold, and then either the attack succeeds or fails, and even if it fails, that you haven't audited it, so you can't. The game kind of just continues. Um, so, anyways, we started out with 62% safety on kind of pure trusted monitoring. It has approximately 100% usefulness, a little bit different because, well, low level reasons, but uh, I mean, Monte Carlo stuff. Um, but if you defer to trusted 5%, you can buy, 12% safety, which is pretty good. And, deferred trusted 10% buys you like 20% more safety. So you can do quite a lot better if you're willing to trade up just a little bit of usefulness. Um, and so this gives you a safety usefulness curve where, before this is like the 62% safety and basically 100% usefulness. And then as you sort of defer to trusted more, this is the green line for right now. You give up a little bit of usefulness, but your safety score goes up quite a lot. And so, control research, like you don't just care about safety, you want your protocols to be useful. So you kind of want this curve of safety usefulness to be like as far out as possible. And these purple and red lines are these more advanced protocols, which we'll talk about in a bit. Oh wow, I'm almost out of time. Okay. Let's see.
I
Yeah.
think you could just keep on going for, I mean, don't be too concerned about it, please.
Oh, okay. Okay, yeah. Okay, I'll you just mention some of the other protocols. Yeah, they tried trusted monitoring with untrusted justification. We're like, GPT 3.5 asks GPT 4, like, why did you do this? On a seemingly backdoor thing, and then GPT 4 kind of makes up reasons for why that backdoor needed to be there, why it's actually benign. So this actually didn't help safety. This is something that didn't work very well. But something that did work is, when GPT 3.5 sees a suspicious code snippet, it doesn't like regenerate from scratch the way deferred trusted works, but it just like edits that particular snippet by itself without hearing anything more from GPT 4. And this actually just did really well. Um, so it's that was encouraging. Like some protocols don't work, some protocols do work pretty well, and it's not obvious until you go out and test them. So that's this purple line is trusted editing, which yeah, just clearly improved on just regular deferred trusted. Um, and yeah, I mean, there's some qualitative trends about how do you write backdoors that fool weaker LLMs. What GPT-4 mostly did here is just add this kind of conditional statement that looks like it handles an edge case of the problem when it's really not necessary. Um, at least that's my understanding of how a lot of these backdoors went. Another thing you can do that wasn't in this paper is you kind of like if you have a very long context, which is like more realistic, if you have an AI that's like kind of building up your code base of like thousands of lines at a time, you want, maybe like two or three far away pieces of code that interact in ways that are very not obvious. Um, and yeah, the some follow work kind of looked at things more relevant to this. Um, and yeah, I mean, there's kind of if you read about the International Obfuscated C Code Contest, which is just about humans just making crazy things with code that are like very hard to spot. There's kind of a hobbyist industry there. Um, but yeah, some things that I want to say is like the efficacy of the different control measures is not obvious until you actually test them. On the other hand, you don't want to take all these safety numbers exactly literally because the real situation can be different in quite a lot of ways. And something I want to highlight is trust monitoring and trusted editing might not scale very well as you'd hope. So yeah, I just wanted to talk about this. So, where do these trusted models come from in the first place? Well, what we mean by that is we mean that like a given model, like current models for the most part, are not egregiously misaligned, first of all. And we can certify that because we can tell that they're just totally incapable of scheming. Like the basically if you're looking at something like GP4, like first you observe it is not passes your propensity evals, and more of those propensity evals actually mean something because it's not capable of like playing the long game of lying across all of those and stuff like that. But in the future models will be capable of that, so our propensity evals will start to not be as meaningful. um so you know, like definitely like most models up to a year ago, like no doubt, definitely trusted in this sense, definitely not capable of scheming. The very recent models, like I think they're probably still like incapable of scheming, like to such an extent, like if they were like egregiously misaligned, we'd probably be able to tell. But it's becoming more of a gray area because eval awareness is very high. Like that's the main capability you need for getting away with scheming, and also just interpreting what's going on in the chain of thought is less reliable with kind of outcome-based RL. And yeah, the field doesn't actually have like a clear-cut definition of trusted. Um, but uh, something we do know is like eventually they'll cross this line where they will be capable of faking lots of propensity evals. And once they cross that line, that's when we'll have our most powerful trusted model, and then the untrusted models will kind of continually get smarter. And then after that, these protocols which rely heavily on trusted labor will become maybe less efficacious. And so that's sort of the motivation for untrusted monitoring. Okay, so I think I'm gonna skip this for a day because next week we'll just talk more about that. That's what next week's paper, and that's what my paper is about, extending what they did with untrusted monitoring. Um, some other things I want to say. Want to since the evals reading group, I want to compare control evals with dangerous capability evals. So a way to define what a control eval is, it's a dangerous capability eval, except where you're evaluating the model under special countermeasure, under specific countermeasures. And conversely, you could think of a dangerous capability eval as a control eval where you don't have any control measures. So it's kind of just a broader class of things. And if I may just be a little bit mean here and just try to stir the pot a little bit, with dangerous capability evals, you ask like, what's the theory of change for them? You like run your dangerous capability evals, the models keep scoring higher on them. Eventually, they'll kind of cross the line where they become, capable of doing dangerous things. And then what do you do? Uh, Whereas with control evals, the theory of change is more clear. It allows you to see which control techniques actually work and actually like keep control over your AIs for longer than you otherwise would have. Um, and so going back to control versus alignment evals, the thing that makes control evals easier compared to alignment evals is you're just doing a capability evaluation rather than a more conceptually difficult propensity evaluation where it's unclear how you would prevent a model from just faking its propensities. On the other hand, control evals don't scale indefinitely past, to the superhuman level. So we will have to solve alignment eventually. And so we can sort of imagine as capabilities get stronger, eventually they will be able to do dangerous things. And at which point, our DC evals will say that. At which point, we want to make sure they can't. We want to build control measures to ensure they can't. And then eventually they'll reach a higher point where we can't even keep them under control anymore. And at that point, we better hope we've solved the alignment. And you can also, if you want to think about this even more fine-grained, maybe trusted monitoring is the stuff relevant to this range, whereas untrusted monitoring, which again we haven't talked about it, but it has more potential for scaling a little bit further. And so, you're building like a safety case for your AIs over time. Right now, the safety cases, well, that they're not able to cause a catastrophe at all. In the near future, maybe it's like they can cause a catastrophe if we didn't even try to control them. But the argument is like our control measures keep them in check for now. And then, then eventually you just have to make some kind of argument based on alignment. Um, and so, control is like, how can we use AIs to accelerate alignment research during this critical period when AIs will be very powerful, like powerful enough to do quite a lot of research for us, but also perhaps do bad things if they wanted to. Um, yeah, okay, I think I'll probably stop there. Yeah, there's like lots of other stuff in control research. Besides that, Um, I mean, we focused on the prevent AI take over the cyber attack. You can also talk about other threats as well as human misuse. A lot of these techniques are applicable there. Um, yeah, I think I'll stop there.